planets are nearly as common as stars in our galaxy. Among the hundreds of billions of stars that make up the Milky Way, a significant portion are surrounded by planetary systems bound to them by gravity. While many of these worlds look nothing like our own, they still share key characteristics that reveal clues about how they formed. By understanding the life cycles of stars and the evolution of their planetary systems, we gain essential insight into the processes that created them. With this knowledge, we are finally beginning to uncover the events that unfolded during the birth of our solar system. Before exploring its origins, it is important to understand what the solar system looks like today. At roughly 4.5 billion years old, it consists of 8 known planets. The 4 closest to the Sun are small, rocky terrestrial planets, while the next 4 are much larger gas and ice giants. 6 of these 8 planets have at least one moon, and the largest planets have dozens. Some moons are so large and dynamic that they could be considered worlds in their own right if they were not orbiting giant planets. Beyond the planets and their moons are dwarf planets, countless asteroids, and trillions of icy bodies arranged in belts and distant reservoirs around the Sun. The outer solar system is made up of 3 major regions: the Kuiper Belt, the scattered disk, and the vastly more remote Oort cloud. All 3 contain frozen remnants of material that originally formed closer to the Sun but were later ejected outward by gravitational disturbances. The Kuiper Belt begins just beyond Neptune and stretches to around 55 astronomical units from the Sun. Beyond that lies the scattered disk, extending to well over 100 astronomical units. Much farther still is the hypothetical Oort cloud, beginning perhaps 600 astronomical units away and reaching nearly a light-year into interstellar space. These distances are almost unimaginable. Even light, the fastest thing in existence, would take more than 18 months to cross the outer boundary of the solar system. Yet nearly everything interesting in the system, including the only known example of life, lies within a relatively small region less than 50 astronomical units from the Sun, protected from harmful cosmic radiation by the Sun's heliosphere. Today the solar system sits in a calm, orderly state. Each of its planets follows a stable, nearly circular orbit, with the terrestrial planets inside and the giants farther out. For a long time, astronomers believed this structure was typical of most planetary systems. But since 1995, when we first detected planets around other stars, we have found that very few systems are this neat. Planets can be found in wildly different arrangements, sometimes in eccentric or chaotic orbits. It turns out that planetary systems are naturally dynamic, constantly evolving and reshaping themselves over time. Our own system likely behaved the same way. Despite its present order, the early solar system would have been far more active, violent, and unpredictable. We humans appeared far too late to witness this chaotic youth firsthand, but we can still see the fingerprints of the events that shaped it. Observations of thousands of star systems at different stages, from their formation in clouds of gas to their eventual destruction, have allowed us to piece together the likely history of our own system. The model that best fits this evidence is known as the nebular hypothesis, a framework widely accepted by scientists today. While some details remain uncertain, the overall picture is strongly supported. The story begins with a massive, cold cloud of gas and dust drifting through space, made mostly of hydrogen and helium but containing small amounts of heavier molecules, organic compounds, silicates, and volatile substances like water and methane. These immense clouds are unstable and uneven, constantly shifting and fragmenting under their own gravity. As pockets of higher density form within them, these fragments collapse into smaller nebulae called protostellar clouds. It is inside one of these fragments that the solar system was born. For a star to begin forming, something must disrupt the stillness of the cloud. In the case of our solar system, the trigger was likely the shockwave from a nearby supernova. This explosion sent ripples of energy through space, compressing parts of the nebula, stirring it, and causing it to rotate. The shockwave also seeded the cloud with heavy elements forged in the dead star's core. This disturbance awakened not just the cloud that would form the Sun, but many neighboring pockets of gas as well. The Sun was born alongside hundreds of sibling stars in what is known as a stellar birth cluster. As the solar nebula began to rotate, its matter flattened into a spinning disk. Gas spiraled inward toward the center, gradually collecting into a dense core. After about 100,000 years, a hot sphere of gas had formed at the center, a protostar that continued to grow as it drew material from the disk. For a time, the young star was surrounded by a thick envelope of gas that fed and compressed it, heating it further. Eventually, the protostar ignited, not in full hydrogen fusion, but in a weaker process fueled by deuterium. Only stars that accumulate enough mass, about 80 times that of Jupiter, can reach the pressures necessary for true hydrogen fusion. Fortunately, the Sun did. Once the young star began generating outward pressure, jets of gas erupted from its poles, clearing away the remaining envelope. After roughly a million years, the Sun emerged into view as a Tauri star, a young, energetic object still surrounded by a disk of leftover material. During this stage, a brief but critical window opened. The disk had just enough time, about 10 million years, for planets to form. After that, the gas and dust would be blown away or absorbed, and no new planets could ever appear. In the early disk, temperatures near the Sun were far too high for volatile substances to condense. Only metals and silicates could withstand the heat, forming tiny grains of rock. Farther out, where space cooled, water, methane, and other ices could form solids. Dust grains collided and clumped together, forming centimeter-sized pieces, then meter-sized bodies, and eventually kilometer-wide planetesimals. Gravity favored the largest objects, which rapidly grew into planetary embryos. As time passed, these embryos collided violently, generating heat and forming differentiated bodies with layered interiors. This process produced the inner rocky planets. Because silicates and metals make up only a small portion of the nebula, terrestrial planets could never grow extremely large. Meanwhile, farther from the Sun, beyond the region known as the snow line, ices were plentiful. Planetary embryos in these colder regions accumulated much more material and quickly grew massive enough to attract hydrogen and helium, forming giant planets. Gas giants like Jupiter and Saturn developed thick layers of compressed gas, while the smaller ice giants, Uranus and Neptune, formed later and retained more ices than gas. These giants dramatically reshaped the young solar system. As they grew and migrated, their gravity scattered leftover material, forming the Kuiper belt and eventually the distant Oort cloud. They also disrupted the asteroid belt, preventing it from forming another planet. In the inner system, dozens of planetary embryos collided over tens of millions of years. Mars likely formed from only a few collisions, remaining small. Mercury appears to be the remnant core of a once larger body stripped of its mantle in a catastrophic impact. Earth and Venus grew larger, developing hot interiors, magnetic fields, and early atmospheres. About 500 million years after formation, Jupiter and Saturn entered a powerful orbital resonance, altering the orbits of the outer planets. Neptune was pushed outward into the young Kuiper belt, scattering icy bodies in all directions. Many were launched into distant space to form the Oort cloud, while others were sent inward as a barrage of comets and asteroids that bombarded the planets. During this violent era, water-bearing comets repeatedly struck the terrestrial worlds, delivering the water that eventually formed their oceans. Remarkably, there were once not one but 3 blue planets in the inner solar system. Early Mars was warm enough for rivers and lakes, perhaps even oceans. But Mars cooled quickly, its core solidified, its magnetic field failed, and its atmosphere was stripped away. Venus, larger and more active, may have remained temperate for 2 billion years. As the Sun brightened, however, Venus entered a runaway greenhouse effect. Its oceans evaporated, its atmosphere thickened, and its surface became the hottest in the solar system. Earth alone remained in the narrow zone where conditions could stay stable for billions of years. Complex life emerged and ultimately became capable of contemplating its own origins. Yet even Earth is not permanent. The Sun is still evolving, slowly growing hotter and brighter. One day balance will be lost, and the solar system will enter a new era of transformation and destruction, a future in which Earth may no longer survive. But for now, we live in a moment of rare stability within a system shaped by chaos, collisions, migration, and cosmic chance, a place forged in fire, sculpted by gravity, and filled with stories written across billions of years.